Hey guys, this next video is going to launch the start of our next unit, which is going to be an extension of what we did with polynomial functions. But in this unit, we're going to be looking at a lot of specific theorems, which are essentially mathematical laws dealing with polynomials. And two of those we're going to look at today. Before we get into that, though, I just want to review a little bit of a concept that's going to be coming up a lot in this unit here, and that's something that we just did in the last lesson. And that is synthetic division. So hopefully, in the last couple of days, you haven't forgotten this. I want you to pause the video really quickly, and just this first review problem at the top of this page, I would like you to do this. So you're going to use synthetic division to divide negative 3x squared plus 5x plus 4 by x minus 3. Please do that in the space provided here below. Okay, so hopefully when you did your synthetic division, you got this for your work. X minus 3 goes into negative 3x squared plus 5x plus 4 with a remainder of negative 8. So now what I'd like you to do is I'd like you to pause the video again, and this time I'd like you to evaluate the following polynomial function, f of x equals negative 3x squared plus 5x plus 4. So you're going to find f of 3. So take a moment and complete that, please. Okay, and so if you do your evaluation on this function for f of 3, you should get an output of negative 8. Now, it may seem odd that I had you do a synthetic division problem and then a function notation problem here, but you'll notice there's something a little bit neat about the answers that you get for these two different problems. The answer that you get for f of 3, you'll notice hopefully matches the remainder you get here when dividing that same exact polynomial, negative 3x squared plus 5x plus 4, by the quantity x minus 3, which means we also have to use a positive 3 for our synthetic division. Okay, and that's not actually a coincidence right there. That's actually leads us to our first theorem we're going to look at in this unit, and that's called the Remainder Theorem. And what the Remainder Theorem says is this. It says you can take any polynomial, okay, we'll call it p of x, and you can divide it by the quantity x minus r. Okay, and so when we divide that polynomial by the quantity x minus r, we're going to get a remainder, okay, some number, okay, and this right here would represent a remainder, okay, and that remainder is special because that remainder is actually the same as if you took that r value here and you plugged it in for your input for x and evaluated the function, which is what we did up here, okay. We divided our polynomial, okay, by the quantity x minus 3, and we got a remainder of negative 8. And then we took that 3 value and we plugged it in for x into the same function down here, which also gave us a negative 8 for an output. So that is what the remainder theorem is basically saying. It's saying that when you do synthetic division on a polynomial, the remainder matches what you would get when you evaluate that function for that same input value, in this case up here a 3. So now let's practice that concept with some examples. You'll notice this gives us a really nice way of evaluating functions that have a large degree, because now we're going to use this process. It's called synthetic substitution to evaluate each of these functions, right, rather than just plugging in the inputs and doing order of operations. Okay, so let me show you how this works. We all know, hopefully, that if I gave you the function f of x here and asked you to find f of 4, that one way you could do that is just by plugging in a 4 for x everywhere and doing order of operations. Okay, another way is, of course, using your calculator, but let's say I don't have my calculator with me. Okay, what would be a quick way of figuring out what f of 4 is without necessarily having to go through plug in and do all of my order of operations? Well, I can use this process called synthetic substitution, which just means I'm going to do synthetic division with my 4 on the polynomial 3x to the 4th minus 2x cubed plus 5x minus 2. So I'll have a 3 here, I'll have a negative 2, I'm missing an x squared term, so I need a 0 for my placeholder, a 5, and then a 2. And so when I do my synthetic division, let's see, 165 times 4 would be 660, so I get a remainder of 662. And that remainder there, 662, is actually the same as what I would get if I plugged in a 4 in for x here. So f of 4 is equal to 662. Okay, let's try that with number 2, g of negative 1. So I'm going to do synthetic division with a negative 1, and then this polynomial. I'll need a 4, a placeholder of 0, a 2, a 1, another placeholder of 0, and a negative 1. And this time I get a remainder of negative 6. Okay, so again, that means that if I plugged in a negative 1, okay, into this function for x, my output would be negative 6. So you can see this is a really, really nice quick method, again, especially if you don't have your calculator with you, to find really any output for any kind of polynomial function. Okay, this moves us on into a little bit more vocabulary here. Okay, so when you divide a polynomial by one of its binomial factors, which is what we do when we do synthetic division, the quotient is what we call a depressed polynomial. Okay, it's not depressed because it's sad. It's depressed, meaning that it's a little bit shorter than the original polynomial. A depressed, so this right here would be an example of a depressed polynomial if we made that 3x cubed plus 10x squared plus 40x plus 165. Okay, the shorter version, if you will, of the polynomial. So a depressed polynomial always has a degree that is 1 less than the original polynomial. Okay, this moves us on into our second theorem for the day that we're going to talk about, and this theorem is what's called the Factor Theorem. We hit on this a little bit in the last unit. I kind of highlighted this concept, but we didn't really make it a huge focus. This unit here is where we're going to really start to look at this particular theorem. So a polynomial has a factor of, I'm going to say, x minus r, if and only if, the value of f of r is equal to 0. And so here's the gist of what this is saying. This is saying that x minus r is a factor of this polynomial only if r is a 0 of the polynomial. Okay, so x minus r is a factor only if r is a 0. Okay, what is a 0? It's a number that if you plugged it into the original function, it gives you an output of 0. Okay, so x minus r is a factor if r is a 0. Okay, that's all that factor theorem is saying. And so we're going to apply that now to a few examples. So example 3 right here, we're supposed to do two things. The first thing we're supposed to do is determine whether x minus 5 is a factor of this polynomial here. Okay, so if in order for x minus 5 to be a factor, then positive 5 has to be a 0 of this polynomial right here. Okay, so one option I have is plugging positive 5 into x cubed minus 7x squared plus 7x plus 15 for x. The other option I have is using my synthetic substitution. So doing synthetic division with the positive 5 on that polynomial. And I'm going to choose that option right there. So I'm going to have a 1, a negative 7, a 7, and a 15. And again, my goal is to get a 0 for my remainder. Because if I get a 0, that means that 5 is a 0 of the polynomial, and therefore x minus 5 is a factor. So let's see. I do my synthetic division, and I get a negative 15 here when I multiply, so that gives me a 0 for my remainder. So that tells me, yes, in fact, x minus 5 is a factor of that polynomial. Okay, so now I can take this depressed part, so to speak, and I can start factoring this polynomial. Okay, I know x minus 5 is a factor, and then my depressed polynomial here is x squared minus 2x minus 3. Okay, so if we multiplied these two together, we would get this original polynomial here. And now I can factor my trinomial here that I got into x minus 3 times x plus 1. So synthetic division can actually help us with our factoring skills as well. If we already know one of the factors, we can use synthetic division to find some other factors. Okay, so this is the factorization of that original polynomial there. Okay, last thing is we're going to use the factor theorem now to do the opposite of factoring. This time, I'm going to give you a couple of polynomials where you know the zeros, and I want you to tell me what the original polynomial was. Okay, so let's look at number 4 right here. I'm giving you 3 zeros. I'm telling you I have some polynomial here with zeros at -2, +2, and +3. Your job is to write the polynomial function in standard form that would have those 3 zeros. Okay, so we're going to use our factor theorem to help us. Factor theorem says that if, for instance, -2 is a 0, okay, then x minus -2 is a factor of the original polynomial. So if x minus -2 is a factor, that means x plus 2 is a factor. Okay, so that's one of the factors of my polynomial. +2 I know is a 0. Well, if +2 is a 0, that means that x minus 2 is a factor. And finally, +3. If I know +3 is a 0 of my polynomial, then x minus 3 is a factor. So now I'm going to take each of these 3 factors here, and I'm going to multiply them out, and that's going to give me the original function. So that means I'm just going to FOIL. Okay, so we have x plus 2 times the quantity x minus 2, which we know hopefully is x squared minus 4. That's a nice difference of squares there. And we're going to multiply that by the quantity x minus 3. So this would give me x cubed minus 3x squared minus 4x plus 12. Okay, so this would be the polynomial function in standard form that has those 3 zeros, -2, +2, and +3. Okay, and now I'm going to do the same thing for number 5. Number 5, I've given you 4 zeros. I've given you zeros at -3, -3 again, +2, and +3. Okay, well, I could have just written -3 multiplicity 2. Okay, again, anytime a function has repeated zeros or a multiplicity for a 0, that just means it has those factors repeated that number of times. So since I wrote a -3 here twice, that means that x plus 3 is a factor twice for this polynomial. We also know that x minus 2 is a factor from our +2 there, and we know that x minus 3 is a factor. Okay, now one trick I've found over the years that helps me when I'm multiplying several binomials together is if I can multiply any conjugates by each other, I'll do that, and I'll do that first. Okay, so I have an x plus 3 here and an x minus 3 here. If I multiply those together, I get x squared minus 9. Okay, so that makes it a little bit easier in terms of my multiplying here. I'm also going to multiply x plus 3 times x minus 2. And when I FOIL that out, that would actually give me x squared plus x minus 6. Okay, so now I have this binomial times this trinomial that I need to multiply together. And so let's see, I get x to the 4th plus x cubed minus 6x squared minus 9x squared minus 9x plus 54 when I multiply this out. So this gives me a final answer of f of x equals x to the 4th plus x cubed minus 15x squared minus 9x plus 54. Okay, so those are your both factor theorems and remainder theorems. Again, we'll be talking about a lot more theorems in the coming lessons, but hopefully these two didn't hurt your brain too much. If you have any questions, as always, please be sure to ask those the next time you see me during class. And until then, have a nice day. You're all wonderful people. Take care.